Welcome, focused learners, to another explainer. I am absolutely thrilled to have you here today because we're tackling a true classic. It's one of those topics that really separates the beginners from the pros when you're sitting at a software engineering interview panel. Today, we're mastering Python memory allocation. And specifically, we're diving into the notoriously tricky mechanics of copying lists. Listen, if you've ever had a bug where you change data in one place and it mysteriously alters somewhere completely different, well, you know exactly why we're here. We've got a fantastic, highly structured slide deck prepared for you, so let's get our mental whiteboards ready and just jump straight into it.
Okay, so imagine you're sitting right there in the interview hot seat. The panel looks across the table at you and asks this deceptively simple question. They say, what happens to the original list if you modify a copied nested list? Now, it sounds straightforward, right? But this question is a trap. It's designed to test your fundamental understanding of memory addresses and data corruption. And frankly, answering this incorrectly, it's a massive red flag for memory leaks in a production code base. So let's look at the syllabus for today. First, the interview hot seat. Second, assignment and sharing memory. Third, shallow copy, the nested trap. Fourth, deep copy, true isolation. And finally, number 5, the interview cheat sheet. All right, kicking things off with section 1, the interview hot seat. To absolutely crush your panel, you have to understand exactly what memory is doing under the hood. And really, this entire explainer hinges on one absolutely vital concept, which is mutability. So a mutable collection, like a Python list, is a data structure whose elements can be changed or updated in memory after it's been created. This is absolutely crucial to keep in mind, because immutable objects, like tuples or strings, they just don't trigger these same memory reference traps we're about to explore. We literally only run into these copying nightmares because lists are designed to be modified on the fly. Moving right along to section 2, assignment, sharing memory. Let's imagine this box of shapes represents our code snippet list1. We simply assign a new variable, saying list2 equals list1. Easy, right? But then we try to modify list2 by dropping a new purple object into it. Take a look at the visual on the right. Unexpectedly, list1 has also mutated to include that new object. So by just trying to update our new list, we've accidentally corrupted our original list. Not good. And this whiteboard diagram brilliantly illustrates exactly why that happens. Let's walk through it step by step. Step 1. Python creates the collection of items and allocates a single memory box or memory location for that list. Step 2. The variable name list1 is essentially just a name tag stuck right onto that box. And step 3, when you use the equals operator to assign list2, well, Python doesn't create a new box. Actually, scratch that, it literally just prints out a second name tag called list2 and slaps it onto that exact same original box. Both variables are just referring to the exact same memory location. Change the contents of the box, and naturally both name tags reflect that change. Now for section 3, shallow copy, the nested trap. Let's look at a best case scenario first. On the left, we use .copy to create list2. Now, if we take a marker and modify the blue square in list2, notice what happens on the right. Total success! List1's square stays perfectly intact, while list2 gets the update. So for single dimension, flat list, a shallow copy safely allocates a totally different memory location for the new variable. The name tags are finally on 2 separate boxes. At this point, you might be feeling pretty confident, but here comes the panel's pivot. What happens when we have a collection of collections? Like, what happens when we use a nested list, with entirely separate lists existing inside of our main list? Okay, watch this disastrous output. We use our supposedly safe .copy method on a nested list. But when we navigate into the inner box of list2 and mutate it, represented here by this yellow scribble, boom, data corruption. Both lists unexpectedly update with scribble. Our shallow copy has spectacularly failed us. So here's the underlying logic you absolutely must explain to your interviewer. A shallow copy only goes one level deep. It creates a brand new outer collection container, like a new big box. But inside that new big box, it doesn't create new inner boxes. It simply copies the memory references, the object IDs, pointing right back to the original inner items. Both outer lists are technically different, but they are staring at the exact same inner objects in memory. And we can actually prove the outer containers are isolated. If we take list1 and append a completely new nested object to it, think of it like dropping a new block into these hexagonal pillars. List1 gets it, but list2 does not. The outer boxes are definitely separate. The shallow copy trap only triggers when you dig inside and mutate the shared inner objects. All right, let's fix this. Section 4, deep copy, true isolation. To achieve true isolation, you can't just rely on a built-in list method. You must explicitly import the copy library into your Python script. Once imported, you use the syntax copy.deepcopy and pass in your original list. Now, be aware, this is a more memory-intensive operation for sure, but it is absolutely crucial for your data safety. Let's compare this side by side with our previous disaster. We use deep copy on our nested list, effectively locking away the original. When we take a wrench and mutate an inner item of list 2, we finally achieve true isolation. List 2 successfully updates, and our original list 1 remains safely untouched. We've completely prevented the data corruption error. Let's quickly whiteboard the deep copy mechanics. Step 1. Just like a shallow copy, Python creates a new outer list box for list 2. But here is the real magic in step 2. Deep copy operates recursively. It digs into the original list, looks at every single inner object, and creates entirely new inner item boxes in fresh memory locations. The object IDs completely shift at every single level. Step 3. List 2 is mapped to this fully independent, completely cloned memory structure. Finally, let's bring it all together. Section 5, the interview cheat sheet. First off, I want to highlight the number 1. Just remember the single dimension rule. If you're asked about a normal, flat, one-dimensional list with no nested objects, a shallow copy behaves exactly like a deep copy. Seriously, don't overcomplicate it if the data is just flat. So the crucial point is summarized right here on this matrix. I'd highly recommend taking a quick screenshot of this slide right now for your prep. The equal sign always shares memory. The .copy method gives you independent memory for flat lists, but tragically shares inner object memory for nested lists. And .deepcopy guarantees independent memory across the board, no matter how deep the rabbit hole goes. Let's just run a rapid-fire mock interview to lock this in. Flat lists. You confidently answer, shallow copy is fine and highly performant. Do shallow copies isolate immutable items? No, they only copy the references. Best tool to prevent nested data corruption? The copy.deepcopy method, because it recursively generates new memory locations. Just be sure to tell your interviewer that you know deep copies cost more in processing time and memory. To wrap things up, I want to leave you with a final, somewhat provocative question. Imagine you're managing a default user configuration template in a massive e-commerce app. In a complex data structure with hundreds of nested, mutable layers, how confident are you that your data is truly isolated from memory leaks when a user updates their profile? Audit your codebase. Think deeply about where your name tags are pointing, and you'll never fall into the nested trap again. Keep learning, stay focused, and I'll see you in the next explainer.